Okay, friends, let us continue. No, feel out. Fan, no, please. Now let us see the atomic radius of the group 13 elements. Atomic radius. Atomic radius. Let us take the elements in group 13. We know the elements in group 13 are boron, aluminium, gallium, indium, and thallium. As we know, down the group the atomic size increases. Down the group the atomic radius increases. That is quite common. So from boron to thallium, we expect an increase in the atomic radius. We expect an increase in the atomic size. But you consider the atomic size of gallium and aluminium. You take these two elements. Normally, we expect gallium to have larger size than aluminium, because down the group you have studied from top to bottom the atomic size or atomic radius increases. If it is so, according to our expectation, gallium is larger than aluminium. That is our expectation. But the atomic size of gallium, that is found to be 135 picometer. That's only 135 picometer. While that of aluminium is 143 picometer. So what happens here? See, in the case of aluminium and gallium, there is a twist. That is, gallium is smaller than aluminium. Gallium is smaller than aluminium. Why is it so? That is so because in gallium there are 10 electrons in the inner d level. In the inner d level, 10 electrons in the d level. In the d level, 10 electrons are there. And the d electrons have very low shielding effect, very low screening effect. We have studied that the screening effect is in the order S greater than P, greater than D, greater than F. So S is having the highest screening effect or a shielding effect. Here we have the inner d electrons in gallium. The atomic number increases, but the inner d electrons have very poor shielding effect. There is increase in the atomic number by 10 units, but the shielding effect of 10 electrons, 10 d electrons, that is less. So due to the very poor shielding effect of or screening effect of the d electrons, the outermost electrons are pulled strongly towards the nucleus, and so there is a reduction in the size of the gallium atom. Gallium is smaller than aluminium. That is because of the very poor shielding effect of the inner d electrons. Due to the poor shielding effect of the inner d electrons, the outermost electrons are attracted by the nucleus strongly, and there is a contraction in size. That's why gallium is having smaller size than aluminum. The rest remains the same. Now let us think of the melting points. Melting points. Here we have to see the melting point of only one metal specially. And that is the melting point of gallium. You take the case of boron. Boron has very high melting point. Boron, the first member, boron has very high melting point. That is because in boron there is strong attraction between the boron atoms. Very strong attraction between the boron atoms in the crystal lattice, and boron exists as giant molecule, large molecule, and so the melting point of boron is very high, very high. You know, during melting, the atoms or the particles are to be separated. During melting, the atoms or molecules are to be, the particles are to be separated. Melting point, at melting point, there is separation of the particles. But here, in the case of boron, boron is a very giant molecule. It's a very large molecule in which there is strong attraction between the boron atoms in the crystalline lattice points. So, the melting point of boron is very high. Now you go to down the group, you take the case of gallium. Gallium has very low melting point. Very low melting point. You know, the melting point of gallium is almost 30 degrees Celsius. 30 degrees Celsius. That's the melting point of gallium. So what happens during summer season? You know, during summer season, the atmospheric temperature will be normally greater than 30 degrees Celsius. Greater than 30 degrees Celsius. And so, gallium exists in the liquid state, during summer season. Gallium has very low melting point of the order of 30 degrees Celsius or a 303 Kelvin, roughly 303 Kelvin. And so, gallium exists in the liquid state during summer season. If a piece of gallium is kept on your palm, what happens? We know the body temperature is 37 degrees Celsius. Our body temperature is 37 degrees Celsius. But the melting point of gallium is only 30 degrees Celsius. So what happens when a piece of gallium is kept on your palm? What happens? It melts. Gallium melts when kept on your palm, because the body temperature is 37 degrees Celsius, while the melting point of gallium is only 30 degrees Celsius. Similar is the case with the cesium also, the alkali metal cesium. The melting point of cesium, that is less than 30 degrees Celsius. Around 30 degrees Celsius. And so cesium also exists in the liquid state during summer season. Similarly, when a piece of cesium is kept on your palm, it melts. Because the melting point is less than 30 degrees Celsius only. So it melts. So remember these two metals, gallium and cesium. They exist in the liquid state during summer season because they have very low melting point of the order of 30 degrees Celsius. And so when these metals are kept on your palm, they melt because our body temperature 37 degrees Celsius is higher than the melting point of gallium as well as cesium. Okay, so that's about the melting point of the elements, especially this one, that is gallium. You remember gallium and boron. Boron has very high melting point. Very high melting point. Because boron exists as a giant molecule, large molecule, giant molecule with a very strong attraction between the atoms. So in the crystal lattice, the atoms are held strongly, and so boron has very high melting point. Then gallium has very low melting point. Okay. Let us take some of the compounds of boron. For example, BF3 and BCl3. We take these compounds of boron. All these compounds are of a special interest. You draw the structure of a BF3 molecule or BCl3 molecule. You know BF3, see the structure of a BF3, see it is like this. So like this. It's a planar molecule, trigonal planar molecule. Trigonal planar molecule. If a molecule is trigonal planar, what should be the hybridization of the central atom? Here boron, what should be the hybridization? It is not for the fun we have studied the hybridization. We have to apply this here. We have sp, sp2, sp3. Okay. So trigonal planar, then there is sp2 hybridization. Boron has sp2 hybridization. Similarly, you take a boron trichloride, BCl3. That is also a trigonal planar molecule. Trigonal planar. That is also due to the sp2 hybridization to boron. Now, you just look at the boron atom, the central boron atom. Around the boron atom, there are only 3 covalent bonds. 3 covalent bonds means 3 into 2, 6 electrons. Only 6 electrons are there in the outermost level of boron. That means boron has not completed its octet. And such a molecule is electron deficient molecule. Electron deficient. That means the central atom has not completed its octet. Here there are only 6 electrons in the outermost level of the central atom boron. So it is in need of 2 more electrons to complete the octet. So it is an electron deficient species. This electron deficient species can accept electron pairs. It can accept electron pairs. And we know electron pair acceptor is a Lewis base. I'm sure that you have forgotten all these things regarding acids and bases. The Lowry-Bronsted acid theory, that is protic acid theory. Then there is the electronic concept, that is the Lewis acid base theory. So here electron pair acceptor. Electron pair acceptor is an acid, not base, sorry. It is an acid. Electron pair acceptor. So it is a Lewis acid. Electron pair acceptor, say Lewis acid. BF3, BCl3, etc. are electron deficient. They can accept electron pairs. And electron pair acceptor is a Lewis acid. We know Lewis base, that is electron pair donor. So what happens when BCl3 reacts with ammonia, NH3? Ammonia. In ammonia, on the nitrogen atom, there is a lone pair of electrons. And say these two react with the formation of an adduct. Say NH3, here Cl, and this is tetrahedral. The structure is changed. Say it was trigonal planar, BCl3, trigonal planar, BF3, trigonal planar. All these geometries are due to the sp2 hybridization of boron. Now, boron is electron deficient. It can accept a pair of electrons. So BCl3, BF3, etc. can act as a Lewis acid. Electron pair acceptor is a Lewis acid. Ammonia is a Lewis base. That is lone pair of electron. And the electron pair donor is a Lewis base. So BCl3 or BF3 reacts with the Lewis base NH3 with the formation of say BCl3 NH3 adduct. BCl3 NH3 adduct is formed. In BCl3 NH3 compound, there is a tetrahedral structure for boron. Boron attains the tetrahedral structure. So remember BF3 and BCl3. Similarly, boron hydrides also. They are electron deficient. So they can accept electron pairs. Electron pair acceptor is a Lewis acid. So BCl3, BF3, etc. can act as electron pair acceptors or Lewis acids. Here, ammonia, Lewis base, and there is reaction between BCl3 and NH3 or BF3 and NH3. And in the adduct formed, the compound formed, there is a tetrahedral structure. So aluminum, that is below boron. Boron, aluminum, gallium, indium, thallium. That is the group. Now you take aluminum compounds. For example, aluminum salt, aluminum chloride. You take aluminum chloride. AlCl3. Usually we write aluminum chloride as AlCl3. Aluminum chloride, AlCl3, it is written. But aluminum chloride is also AlCl3, that is also electron deficient. It is also electron deficient. And so it is also a Lewis acid. It can see the structure. Say aluminum, chlorine, see chlorine, AlCl3. Aluminum has not completed its octet. There are only 3 covalent bonds around aluminum, and there are only 3 into 2, 6 electrons. It's not completed, it's an octet. It is a electron deficient. So it can accept a pair of electrons. So AlCl3 is a Lewis acid. Lewis acid. To stabilize aluminum chloride, what aluminum chloride does? Aluminum chloride AlCl3 dimerizes. It dimerizes. Two molecules are combined together. Dimerization. There is a dimerization. That is Al2Cl6. Al2Cl6. That is to stabilize the molecule. And the stabilization is through chlorine bridge. Say the structure will be like this. Aluminium, then aluminium. There is a chlorine bridge. Here also chlorine bridge. Then Cl, Cl, Cl and Cl. Al2Cl6. Al2Cl6. Say there is chlorine bridge. We have seen such a molecule before. Here there is a chlorine bridge. Do you remember? Beryllium chloride. Barium chloride. In barium chloride also we had seen chlorine bridge. Similarly here also there is chlorine bridge. If you take one part, it is tetrahedral. One side it is a tetrahedral. So it dimerizes, aluminum chloride dimerizes, forming Al2Cl6. That is to stabilize the molecule. And the stabilization is through the chlorine bridge formation. Between the chlorine atoms, there are two chlorine bridges. The chlorine atoms are common to both the aluminum atoms. Okay. Now you think of the reactivity of aluminum. We know aluminum is a highly reactive metal. No doubt. It's a reactive metal. But it is not much corroded. It is resistant to corrosion. Aluminum is resistant to corrosion. Why? Due to corrosion, atmospheric oxidation, a protective film of aluminum oxide is formed. A protective film, Al2O3, protective film, protective coating, a protective film or a protective coating of aluminum oxide is formed on the aluminum objects, aluminum articles, and hence aluminum is protected from further corrosion. First of all, it is prone to corrosion. The surface is prone to corrosion. That is formation of aluminum oxide. But this aluminum oxide forms a protective coating, a protective film. A very nice protective coating, protective film of aluminum oxide. And that aluminum oxide protective film, protective coating that protects aluminum from further corrosion. So it is prevented from corrosion due to the formation of aluminum oxide film, protective coating, although aluminum is a reactive metal. So this much is enough for group 13. Group 13. The rest is not included in the syllabus. The compounds are not there in the syllabus. So now let us go to the next chapter, that is group 14. Let us go to group 14. Group 14. Group 14. You know, group 14, which are the elements in group 14? Group 14. Group 13, boron, aluminum, gallium, indium, thallium. Then you go to group Group 14. Group 14. The first member in group 14, it is a carbon. And so group 14 is known as carbon family. Carbon family. The first member is carbon. And so this is known as carbon family. Can you read this? Can you read this?
Yes, sir.
Okay. So group 14, that's called the carbon family. Which are the elements? The elements in group 14. Do you remember the elements in group 14? Carbon, silicon, germanium, tin and lead. Carbon, silicon, germanium, tin, SN tin, and PB lead. Say carbon, silicon, germanium, tin, and lead. Down the group, it is like this. Carbon, silicon, germanium, tin, and lead. These are the elements present in group 14. The first member is carbon, and so known as the carbon family. Let us think of the general outermost electronic configuration. The electronic configuration, general outermost electronic configuration. Let us take carbon as an example. Carbon atomic number is equal to 6. And so the configuration will be 1s2, 2s2, 2p2, 2s2, 2p2. Silicon, atomic number 14. Silicon, atomic number 14. So 1s2, 2s2, 2p6, then 3s2, 3p2, 3p2. We have taken two examples from group 14. Now what you can see there? In the outermost level, there is a S2P2 configuration. S2 is common. Say previously it was S2P1. Remember group 13. Group 13. 3 electrons. Group 13, 3 electrons in the outermost level. And those 3 electrons were distributed as S2P1. Now 14, group 14, 4 electrons in the outermost level. 4 electrons in the outermost level. And there will be S2P2. S2P2. So the general electronic configuration will be NS2, NP2, NS2, NP2. So there are 4 electrons. There are 4 electrons in the outermost level. In the outermost level, valence shell, there are 4 electrons. 14, 1, 4, 4 electrons. 14, 1, 4, 4 electrons in the outermost level. 15, 1, 5, 5 electrons in the outermost level. Remember, just correlate all these things. So that you can easily remember. You can easily remember 13, 1, 3, 3 electrons, outermost level. S2, P1. 14, 1, 4, 4 electrons, outermost level. S2, P2. 15, 5 electrons in the outermost level. S2, P3. Okay. So like that. 17, you take group 17. Now you can say, Vidur, 17. How many electrons will be there in the outermost level? Vidur?
5.
17. Sunny, it is 17. 1, 7. Come on. Now you can say. I will say 5.
S2,
Eh?
S2P,
Ah.
5.
Yes, 7 electrons. 7 electrons. 1, 7, 7 electrons, S to P5, correct? S to P5, 7 electrons. So just correlate all these things so that you can easily remember all these points. Don't study it by heart. Make it thorough. You write in your mind itself. You just feed all these things in your brain computer. Upload all these things in the brain computer. And just delete the unwanted substances. The unwanted data must be deleted. And you stock only the highly wanted data only in your brain computer. Otherwise it will be overloaded. You say system is hanging. There is hanging. What do you say that? It is full of the data. So then what do? You delete some of the data to create space. To create space into memory, what do? You delete some of the data. Similarly, you delete the unwanted data from your brain computer. It's a computer. Brain is a computer. You are gifted with such, say, a very good system, working system. Make use of it. Make use of it. If you are not using it properly, what will happen? It will be corroded. It will be corroded. Yes, the problem is there. So you do exercise always with your brain computer. Okay, come back to this. So in the group 14, 4 electrons in the outermost level, and they are S2, P2 configuration. So the oxidation state maximum, we expected 2 plus 2, 4 plus 4. But down the group, plus 2 is more important. There can be plus 4 and plus 2 oxidation states. Oxidation states. Plus 4, because there are 4 electrons in the outermost level. All the 4 electrons can take part in the reaction, and so it can show plus 4 oxidation state. But down the group, plus 2 state is more important. For example, take lead. For lead, plus 2 state is very important. It is predominant. Plus 2 state is predominant. Can you say what the reason is? Vidur, can you say what the reason is? Plus 2 is important. Plus 2. Come on. Forgotten. Punya, please help me.
Inert pair effect.
Inert pair effect of the S2 electrons. So the S2 electrons are lazy as we are, as I am, unlike Vidur. You are all right. I'm talking about me. Okay, I'm very lazy to take part in the reaction. Here, the S2 electrons are also, they are inert. They are lazy to take part in the reaction. That's called the inert pair effect. So due to the inert pair effect of the S2 electrons, only the P2 electrons are involved. That's why it is lead is showing predominantly the plus 2 oxidation state. Okay. Now you come to the allotropy. Allotropy. You know what's meant by allotropy? You have studied allotropy a number of times. You have studied. When we were dealing with organic chemistry, we have studied allotropy. Do you remember? Allotropy. What's meant by allotropy? That is the existence of same element in various forms. So the various forms of the same element. The various forms of an element. Various forms of an element are called allotropes. They are called allotropes. And the phenomenon is called allotropy. The existence of various forms. That's called allotropy, and the various forms are called allotropes. Do you remember the important allotropes of carbon. So many are there, and you have studied 3 crystalline allotropes in the 10th standard as well as in organic chemistry also. Allotropes of carbon. So many are there, and the 3 important crystalline modifications are diamond. Remember now? We have taken this in organic chemistry. It says graphite, catenation. We have already taken that. And fullerenes. So these are the 3 important allotropes of carbon. Diamond is the hardest naturally occurring substance. As you know, in diamond, one carbon atom is tetrahedrally surrounded by 4 other carbon atoms. And there is very strong attraction between the carbon atoms. And so, diamond is very hard. As I said, it is the hardest naturally occurring substance, diamond. It is an insulator of electricity. Bad conductor of electricity because the electrons are not free to move. Electrons are not free to conduct electricity. Diamond. But it is very hard. In diamond, carbon has sp3 hybridization. So there is a tetrahedral structure. Now you come to graphite. Remember, in graphite there is layer structure. The carbon atoms are arranged in layers. In a layer, there will be hexagonal rings. And one carbon atom is surrounded by 3 other carbon atoms. In a layer, there is sp2 hybridization. Now, the layers are very weakly held. The distance between the layers, that is 340 picometer. For a true single bond, a carbon-carbon single bond, it's only 154 picometer. But here the distance between the layers, it comes almost double. It is a 340 picometer. So the layers are held very weakly. Very weak attraction between the layers. So what happens? When force is applied, the layers will be slipping over one another. The layers are slippery. Due to the slippery nature of the layers, graphite is very smooth. Diamond is very hard, while graphite is smooth because there are layers, and the layers are slippery because the layers are held very weakly. W-E-A-K, weakly. Not W-E-E-K-L-Y. Not once in a week, very feebly. It is held very feebly, very weak attraction between the small attraction between the layers. And so the layers will be gliding over one another. And so graphite is smooth. Another thing, the electrons between the layers are mobile electrons. And due to the presence of the mobile electrons between the layers, graphite is a good conductor of electricity. Diamond is an insulator of electricity, while graphite is a good conductor of electricity, because in graphite there are free mobile electrons between the layers. So graphite is a good conductor of electricity. Now you come to the fullerenes. Fullerenes have cage-like structure, cage-like structure, fullerenes. They are clusters of carbon atoms. For example, C60, C70, etc. A cluster of 60 carbon atoms, a cage of 60 carbon atoms, or a cage of 70 carbon atoms, cage-like structure. That means it is hollow. It is hollow. Only on the surface of the cage there are carbon atoms. Carbon atoms have sp2 hybridization. sp2 hybridization. The carbon atoms are seen on the surface of the cage. For example, you take a C60 fullerene. It has the shape of a football, a soccer ball, spherical. Soccer ball. Inside is hollow. It is hollow. And on the surface of the soccer ball, football, 60 carbon atoms are arranged. So it is having cage-like structure. Say C60 fullerene, it has got the shape of a soccer ball, and so it is known as buckyball. Buckyball fullerene. And C60, as you know, as you have studied in the 10th standard, C60 is known as Buckminster fullerene. Do you remember? You can recollect it now? No? That's called a Buckminster fullerene. See, the name is coming from Buckminster Fuller. The architect. See, in his constructions, an architect, in his constructions, at the top of the building, we can see the domes. You think of the mosque. In mosque, Taj Mahal. See, at the top there are domes. See, domes, spherical shaped domes are there. So in the constructions of Buckminster Fuller, there were a large number of domes. And due to the similarity in shape of C60 fullerene, it is known as Buckminster fullerene. So the word is coming from Buckminster Fuller, the architect. And it is a C60 fullerene. It is having the shape of a football, spherical shape, soccer ball. Soccer ball is a football. Okay? And it is also known as buckyball. Buckminster. From that the buckyball is coming. Buckyball. So buckyball fullerene. Okay. So that's about the various allotropes of carbon. Among all these allotropes, graphite is the most stable one. Thermodynamically, the most stable allotrope is graphite. It is the most stable allotrope of carbon, graphite. So it finishes the allotropes of carbon, and by that it finishes the chapter. Same group 14 carbon family, and it finishes our chemistry topic for the year +1. Say, I'm very particular that